Hello, beautiful men and women of the world. Thank you for coming to my calculus lecture and learning a little bit about calculus. Today, the topic that we are going to be covering is the chain rule. Everyone say, yay, chain rule. I love the chain rule. The chain rule is so great. This is, again, based on the OpenStax Calculus 1 textbook. Great resource, free resource. If you have any more questions, want to learn more, want to see some of the proofs for some of these concepts, I would recommend you going onto that website and checking it out. The book is amazing. So, chain rule, right? Why do we have the chain rule? I know that many people don't like math and they don't want more rules, but the chain rule does a lot, gives us a lot of help. So we have to understand that functions do not exist in a vacuum, right? In our previous video covering derivative rules, we did not have a use case for when, let's say, a function was being squared, or if the function was, we had a function inside a function, right? We don't have a clear rule on that because different functions do different things. So if we were to have a specific rule for every interaction between two or more functions, we would have infinite rules. I don't know about you, but infinite is a lot, and I don't have time to remember infinite rules. So if we can describe the behavior between certain types of functions when they're being multiplied, when they're inside, like subsumed with each other, when they're composed with each other, then we can do some pretty cool stuff. We don't have to remember an infinite number of rules because our brains aren't that big. Everyone who takes calculus is smart, right? You're smart, capable, and able. No one is smart enough to remember an infinite number of rules. So moving on to chain rule, right? What is a chain rule? So the chain rule basically states that the derivative of a composite function is the derivative of the outer function evaluated at the inner function times the derivative of the inner function. So what does this mean? What exactly does this mean? So in other words, right, we'll let f and g be functions for all x in the domain of g for which g is differentiable at x and f is differentiable at g of x. The derivative of the composite function h of x, which is, f composed of g, or f of g of x. The up here where it says x is in the domain and then g is differentiable at x and f is differentiable at g of x. This makes sure that we just don't catch any hitches. Usually this won't be an issue if you have a function composed with another function. Generally, the chain rule will be applied. So again, h of x, the derivative of h of x, h prime of x, is equal to f prime of g of x times g prime of x. So alternatively, so this is our Newton notation, this is our Leibniz notation, right? If y is a function of u and u is a function of x, then dy dx is equal to the product of dy du and du dx. And we can see that this is true, right? Because if we were to multiply these out, these would cancel out, and then we'd be only left with here and here. So you can believe me, because sometimes we can treat these like fractions. Sometimes we just treat it like an operator, but here we're treating it like a fraction a little bit. But this use case doesn't come up as much when you're using chain rule. It's really here that we want to focus on. This is where our money's made. So how will we use the chain rule, right? We have this great little these great little rules, but it's not always that simple just to know the rule. We have to know how to apply it, right? So when differentiating h of x, which is f composed of g of x, we need to first identify the f of x, and then we need to identify the g of x. So we need to see where we need to split them off. I like to, on my paper, just write f of x is equal to this, g of x is equal to that, because that'll make everything easier. So then we'll find f prime of x, or the derivative of f of x, and evaluate it at g. So this means that we'll find the derivative of f of x, and then anywhere there's an x in that, or whatever variable we're differentiating with respect to, but wherever there, generally it'll be x. Wherever there's an x in that equation, we're going to go ahead and apply our original g of x. And then we'll find our g prime of x, and we'll find the derivative of g of x. And then once we have this term and this term, right, we can multiply them together to find ultimately the derivative of h of x. And then we'll simplify, because sometimes what we might have to FOIL, might have two polynomials, and we can break things down. Chain rule is not a one-time thing, right? So we can have something like f of g of h of k of x, right? 1, 2, 3, 4. We want to work from the inside out, right? So we'll find what f of x is. Once we find what f of x is, we'll find f prime, right? And then we'll evaluate it at this, and then we'll find the derivative. So then we have to use chain rule again, and then we'll have to use chain rule again, and one more, and this is really the last time. But when we do this, we can do it a number of times, which helps us solve multiple compositions. It's not just a one-time thing. A lot of the times you will see just this simple, like a function composed of another function, but that's not always the case. So here we will work this example. I will see you in the real world.
All right, this is our first chain rule problem. So what we'll have to do is identify f of x and g of x. But before we do that, I don't want to do any quotient rule shenanigans. So I'm going to rewrite this as 3x squared plus 1, the quantity to the negative 2. And that'll make this a little easier. So then we now know that our f of x, our outside function, is equal to x to the negative 2. And we know that our g of x is equal to 3x squared plus 1, right? So we'll end up having to take the derivative of both of these. So f prime of x, do our little power rule, negative 2 x to the negative 3. And here, g prime of x is going to be equal to 6x. So then we can go into our f prime of x evaluated at g of x, so our f prime of g of x times our g prime of x, or as people say, the derivative of the outside evaluated at the inside times the derivative of the inside. So we have our negative 2, and then we'll put our original g of x in there, 3x squared plus 1 to the negative 3 times the derivative of g, which is 6x. We can simplify this, so this is going to be negative 12x all over 3x squared plus 1, the quantity cubed. So this is our answer for h prime of x. There you go. Simpler, easier than it looks.
All right, we're back from the real world. Moving on, we'll work another example. Here's our other example. This one may not look, it looks a little tricky, but there's a tip to it. So I will see you in the real world.
All right, here is our second chain rule example. You may say, this only looks like one function, but it isn't, because mathematicians are lazy, and we don't want to write as much. We want to write as little as possible, because we write a lot, right? So I want to rewrite this one in a similar vein to the way that we rewrote the last one. So this is the same thing as saying sine of x cubed, right? These mean the same thing. So here we know that our f of x is equal to x cubed. We know our g of x is equal to sine of x. So then we'll take the derivatives. This will be f prime of x is equal to 3x squared. And here, g prime of x is equal to cosine x. So now that we have this, we can do our f prime of g of x times g prime of x, right? So we'll have 3 times sine x squared times cosine x. We can simplify this a little bit, so this ends up being 3 sine squared x cosine x, and that ends up being the derivative of our function. Like I said, easier than it looks.
All right, now one last example, something similar. We're still dealing with our trig functions. We have this here. I will see you in the real world And if I forget to in the real world, please like, subscribe, comment, do all these great things. If you have any questions, message me, email me, leave them in the comments. I'll be more than happy to answer. I love calculus. You should love calculus too. I will see you in the real world.
All right, here is our last and final chain rule example. So luckily this one, we don't really need to do any shell game. We can tell that our f of x is going to be equal to cosine x, and our g of x is going to be equal to 5x squared. Wonderful, wonderful, wonderful. So now we'll have f prime of x be negative sine x, and we'll have our g prime of x be equal to 10x. So here we can, again, it's just our f prime of g of x times g prime of x. So we'll have negative sine of 5x squared times 10x. And then we can rewrite this to be negative 10x sine 5x squared. And this ends up being the derivative of our function. Like I said, I'm sure I already wished you well, but if this is our last example, this is the last thing you see. Thank you for spending the time today to learn a little bit more about calculus. Go forth, be bountiful with your newfound knowledge. I hope I was able to assist you in some way in your educational journey. I love math. I think you should love math. Math is a great thing. Go like, comment, subscribe. If you have any more questions, email me, do all that good stuff. I'd love to hear from you. I'd love to help you out. Yeah, thank you for taking some time today to learn about chain rule.